How do electric circuits, conductors, and insulators work? Engage your brain. We're going to come back to this at the end of this video. Active reading. Lesson vocabulary. List each term. As you learn about each one, make notes in the interactive glossary, which is right here. You will write these on your paper. Cause and effect. Some ideas in this lesson are connected by a cause and effect relationship. Why something happens is a cause. What happens as a result of something else is an effect. Active readers look for effects by asking themselves, what happened? They look for causes by asking, why did it happen? Some go with the flow. Would you be surprised to see the prongs on an electrical plug made of plastic? You should be. There's a very good reason why plugs and electrical cords are made of certain materials. As you read these 2 pages, underline the definitions of key words. When it comes to working with electricity, knowing the properties of materials is important. Some materials allow electricity to pass through them freely. Others block its flow. Conductors and insulators. You would do well to stay away from electrical poles. They're safe enough when they're in good working order, but if one of these wires they carry were to get free, you'd be in trouble. These wires were made of metals such as copper, which conduct electrical energy. This is something you might want to underline right here. Okay. I'm just showing you. All right. Conductors add electricity to easily travel through time. Some materials prevent the flow of electricity. I'm pausing so you can highlight or underline it. These materials are called insulators. Materials such as plastics, rubber, concrete, glass, and wood insulate electrical energy. Their low cost and flexibility makes plastics and rubber great for covering electrical plugs and cords. Identify conductors and insulators. In each box, write conductor or insulator. Copper wire, electrical gloves, lightning rod, electrical tape, and the brightly colored caps are twist-on connectors. They are used to hold 2 or more wires together. These connectors are made of a conductor and an insulator. Where do you think the insulator is? The conductor is. Explain. All you're doing here is you're going to tell me what part of this cap is the insulator and what part is the conductor. That's all I'm looking for. A path to charge. Suppose you flip on a light switch and nothing happens. What's wrong? Active reading. As you read these 2 pages, draw 1 line under a cause and 2 lines under an effect. Electricity requires a closed path to flow. An electric circuit is a complete pathway made of conductors through which electric current can flow. A battery or other electrical energy source makes electric charges in wires. A battery or other electrical energy source makes electric charges in wires begin to move. When the charges reach a device like a light bulb or a fan, they provide energy to make the device work. The path must go from the energy source to the device and back again to keep the charges moving. This is a complete circuit. Parts of a circuit. Opening a switch in a circuit causes a gap so charges can't flow. Closing or turning the switch on closes the gap. Devices in a circuit such as lamps, buzzards, or appliances are called resistances or loads. You can draw a circuit diagram using the symbols in the key. Notice how each device in the circuit matches a symbol in the circuit. So right here, your black lines, and here's your key. It means it's a wire. The yellow squiggly line looks like a heartbeat almost. is down here, but we know that is called a resistance. And if you're not sure what a resistance is, go back and re-listen to this section or read it yourself. A green one is an open switch. Notice this one does not have an open switch. However, a closed switch is closed, and there is a closed switch here. The battery, and a wall outlet we don't have in this one. These are pretty much universal signs or symbols, as far according to my research on the internet anyway. Oh, did I skip a page? Nope, I didn't. All right, electricity changes in circuits. Electric circuits convert electricity to other forms of energy. For example, circuits in this train change electricity into mechanical energy, which is motion, light energy, and sound energy. Thermal energy is also produced from electricity to heat the interior of the train cars on cold days. The hair dryer changes electrical energy into heat and motion as it heats and blows hot air. Draw a circuit. Use the key on the previous page to draw a circuit diagram for a complete circuit containing a battery, a switch, and a resistance. Then explain what energy changes take place when the resistance is a light bulb. So you're drawing a circuit in this box right here, and you have to have a battery, a switch, and a resistance. Then you need to explain what energy changes take place, because your resistance that you have to draw is a light bulb. So a light bulb is changing electrical energy into what? And we talked about these on Monday. So there's two of them that they turn into. All right, which path to take? One path or many. How do electric charges flow through circuits? Active reading. As you read these 2 pages, draw boxes around the names of the 2 things that are being compared. Okay, so you're going to be drawing 2 boxes around things that are being compared. I'll be looking for these. There are many electric circuits in your home. The lights and sockets in one room might be on one circuit. An electric oven uses a lot of electricity, so it might be on its own circuit. There are 2 main types of circuits. First is a series circuit. Can you identify the parts of this circuit? Look at the key at the bottom of this page for help. In a series circuit, electric current has only one path to follow to and from the energy source. In this circuit, current passes through both light bulbs, so they both light up. What happens if one light bulb burns out? The other light goes out too, because this circuit is broken. Circuits at home. At home, you need to turn lights on and off individually. The same is true for other electrical devices. A series circuit only works if all the devices in the circuit are on. So, which type of circuit do you think is mostly used in homes? Where's that load? Redraw the emergency flashlight circuit. Include the missing load that represents the siren. This is what you're redrawing up here, but you need to include the missing load that represents the siren. Hopefully you see that it's right here, but you need to put it somewhere. Okay. All right, parallel circuit. How can you keep the other devices in a circuit working if one stops working? A parallel circuit contains 2 or more paths for electric charges to follow. This emergency flashlight has a light, a radio, and a small siren. Each device is connected to a battery through its own parallel circuit. 3 separate switches are used to turn the devices on and off so that they can work independently of one another. Why it matters. Home circuits. Look around a room in your house. How many electrical outlets, light fixtures, and switches are there? Are they all in the same circuit? How can you find out? Active reading. As you read these 2 pages, draw a line under the main idea. Your home electrical system is a small part of a larger system that includes your city, state, and national region. The electricity that you use at home might come from generating stations hundreds of kilometers away, At home, a network of conductors, insulators, and switches are arranged into circuits. It carries electricity into every room. Many meters of wiring make up your home electrical system. However, there is a small fraction of the amount of wiring it takes to bring electricity into your home. All right, examine the circuits in the diagram. Circle two resistances wired in the same circuit. Box a resistance that is on its own circuit. Changing electrical energy. Many of the forms of energy you see around your house begins as electricity. Television sets and karaoke machines can convert electricity into light, sound, and thermal energy. Fans, blenders, and can openers can change electrical energy into energy of motion. These machines also waste electrical energy as heat and sound. Look at the picture. Can you tell where electrical energy is being changed? Do the math. Interpret a simple graph. The symbol percent means percent, or out of 100. For example, 8% means 8 out of 100. Examine the information in the graph. Then answer the questions below. You've got others is 8%, refrigerator 8%, water heating 12%, computer electronics 9%, lighting and appliances 20%, cooling is 12%, heating 31%. Number 1, which activity consumed the most energy in the home? And number 2, which two activities combine to consume 29 out of 100 units of energy? Sum it up. When you're done, use the answer key to check or revise your work. Label the parts of the circuit. If you need help remembering what these mean, go back in your packet and look. Or you can go back further in this video and watch. Assume that the load in the circuit above is a light bulb. Explain what would happen if you open the switch. What is the cause? Fill in the missing words to describe conductors, insulators, and electric circuits. Electric current easily passes through, such as silver and copper. All metals are good of electricity. Non-metal materials, such as wood, glass, plastic, and block the flow of. Okay, these materials are called the wires connecting the battery, switch, and resistance in a have a at their center to conduct electricity and a covering made of a to make the wires safe to handle. On this page, this is a word play. It's a crossword puzzle. If you need help with this, just raise your hand and I'll come around and help you. But all of these words are in your reading today. If you just flip back in your book, or you can flip through this video. And apply concepts. Select and circle the appropriate equipment that would be safe to use when working with electrical current. Explain why some are safer than others. You do that here. 3, a wall switch is connected to a wall outlet. A lamp with a switch is plugged into the outlet. You turn the wall switch on, but the lamp stays off. Give 3 reasons why this might happen. And 4, analyze the circuit. On the lines below, explain why the circuit isn't complete. Then draw in whatever you need to complete the circuit. And 5, convert this circuit to a parallel circuit that has a light bulb and a buzzer. Show in your circuit a picture of the resistance in each part of the circuit. And 6, in each circuit, electrical energy is being transformed into other forms of energy. Identify the forms of energy produced in each circuit. If you have any questions, please raise your hand and I will come around and help you. 7. Analyze the circuit. Name 2 possible reasons why one light bulb is not lit. 2 reasons, 2 possible reasons. And number 8, circuits convert electrical energy into other forms of energy. Analyze and evaluate the brightness of the light bulbs in the diagrams. Use logical reasoning and empirical evidence to explain the differences in brightness. All right. If you have any questions, again, raise your hand or go back into your reading or go back into this video. Thanks.